Welcome to today's tutorial. My name is Engineer Obaga. Today we want to be dealing with the loading of beam in accordance to Bs8110 Part 1, 1997. Now, in loading of beams, according to Bs8110, there are specifications for the loading of beams, and the specification is gotten from clause 3.53.7 Bs810 Part 1997 Part 1. Now, if you go to that clause, you will see that the code expressly states that the design loads on beams supporting solid slabs spanning in two directions at right angles and supporting uniformly distributed load may be assessed from the following equations. Now, so we are going to do an example on that to see how we can be able to analyze a situation carrying a load. Now, quickly, let's look at the shear force coefficient table. The shear force coefficient table. When we look at the shear force coefficient table, you will discover that it comprises of edge conditions of slabs, 4 edge continuous, 1 short edge discontinuous, and the various aspect ratio for each of those slabs are taken. We have BVX value, and we have BV, beta VX, and beta VY. All right, so we'll look at it. The equations is Vx equal to beta Vx n Lx, and Vxy is also beta Vy n Lx, where we have Bvx as the shear force coefficient in the short direction, and we have Bvy as the shear force coefficient in the long direction. Now, when we want to load this beam, we must consider two things. Number one, the shear force expression, the load expression Vx is used, but the code of practice equally states that in applying this load on your beam, you must ensure that the load is applied at the center of the beam in such a way that the load occupies 75% of the total span of that beam placed at the center of the beam. All right, so what the code invariably says is that, let's consider panel 1. We intend to load beam A. All right, now if you look at beam A, we have two panels attached to beam A. We have panel 1 and panel 3 attached to beam A. Now, the edge condition of the slabs are, for panel 1, you can call panel 1 as continuous edge, two adjacent edge discontinuous. All right, you can describe panel 1 as such, two adjacent edge discontinuous. The same thing with panel 3, two adjacent edge discontinuous, or we can say two adjacent edge continuous, whichever way you want to put it. So we are dealing with panel 1 and panel 3. Quickly, we will look at the case, or we'll look at it. Next, we are going to look at panel 2 and 4, because we intend also to load beam B. This is our beam B, okay? This is our beam B. So we'll load beam number B. So loading beam B, you will discover that we have two panels attached to beam B. We have panel 2 and panel 4. So if you look at the edge condition of panel 2, we can call panel 2 as two adjacent edge discontinuous, while we could call panel 4 as one short edge discontinuous. That's what we call panel 4. All right, panel 4, the short edge there is the distance 3.6 meters. So that is the nature. So what we'll do, we'll load it. Let's just load these beams and see a clear example of how to do that. Now take note, Bs8110 and eurocode 2 makes use of this same method of loading of your beam. So even in eurocode 2, there's still no change as regards to these formulas. The formulas remains the same. Maybe you're wondering if there's a change. There's no change. The formula remains the same. So quickly, let's do an example of this, and let's see how we can load beam A. 3.5. That will give us 1.428. Okay, that is panel 1. Now, have we got to the aspect ratio? What we just need to do is to go to the code. Now, let's go to the code and see what happens. If you look at the code, let's look for on the table aspect ratio of 1.4. We're going to use that. We have two adjacent sides discontinuous. So we'll pick the values there and we're going to write it. Okay. These are beta Vs. We have two. The first one for the continuous edge. So we have continuous edge. This way you're going to see the slab as this. So this way continuity. Here we have continuity. On this direction, there is no continuity. So that's all I have. So we're interested in a continuous edge because we want to load this beam. This is the continuous edge. So we're going to pick the coefficient for the continuous edge. So I will call my BVX for the continuous edge, which I have it to be 0.52. So my BVS here will be 0.52. Okay. Now the next thing I'm going to look for is my BVY. My BVY, I'm going to check it. BVY. Let me check for it. I have 0.45. Okay, so this is what we have for the continuous edge, both for BVY and BVX. These are for the continuous edge of the panel. All right, so this is what we have for continuous edges. All right, so we'll have all these for the continuous edges. So BVX is 0.52 for the continuous edge of panel 1, and BVY is 0.4 for the continuous edge of panel 1. Now we want to load the beam. We want to apply the load. Our N. Let's assume the load on this slab, total load on the slab to be 16. So let's say the ultimate load N is equal to 16.0 kilonewton per meter square. So let's assume this is the total load on this slab. All right. So if we have the total load of the slab to be 16.0 kilonewton per meter square, we've gotten the shear force coefficient for the short and the long span, especially for the continuous edges. We can also have the shear force coefficient for the non-continuous edges. Let's have it. BVX to be equal to BVS to be equal to we have 0.34. So we have 0.34. Then we'll have BVY to be equal to we have it as 0.26. So we have 0.26. So these are for the non-continuous edge, non-continuous edge. All right. So you can see 0.34 and 0.26. If you check 0.34 under aspect ratio 1.4, you see there for two adjacent edge discontinuous, while at the extreme end you will see 0.26 as the coefficient for BVY, beta VY. All right. So non-continuous edge. So we have these two coefficients. So what it means is that wherever we want to load any of the edges, we apply these formulas. All right. Now, like I said before, for the short span of your panel, all right, what I mean for the short span, for example, in our case now we have this panel as panel 1. These are panel 1. Okay. These are panel 1. We have our panel 1 to be 5 meters by 3.5. Now there are beams here. We know that this beam is beam A. That is what we're interested in. We want to load. Okay, remember we have beams on the four side of this slab. So we have them as this. So now we want to load this beam. We want to carry the load from this slab to this beam. So remember the original theory, the yield line theory, we have the yield line of failure of this beam as this. Remember that the yield line is this. But the original formula for this is a triangular and a trapezoidal load. But the code of practice Bs8110 has modified this to give us this shear force coefficient for easy calculation of the load. So let's go over to this. We have Vx equal to beta Vx n else. Now this Vx represents the load on the long span of the beam. So take note, edge, which is beam A. So since we are losing the continuous edge, we'll look for our beta Vx value for the continuous edge. Now, if you look at it, the continuous edge will have our beta Vs value to be 0.5. So we want to load the continuous edge now, so we'll go. All right, so we just did the interpolation of the values of 1.7, between 1.7 and between 1.75 and 1.5 from the table. So what we did is just an interpolation, and we'll have the mid values as this. All right, so these are the values after interpolation. So we're treating this span 6 meter by 3.5 now. Edges of this slab, but in loading of beam B, we are much more interested in what? In the continuous edge of the long span. And of course, I've told you before that the continuous edge of the long span, the formula is Vx beta Vx NLX. So we are going to load beam V. So for beam V, beam B, we're going to have the load on beam V to be what is the for the continuous edge? We have BV. So we have BV coefficient here for the continuous edge is 0.565 times the load on the slab 16 times the length of the short span, which is 3.5. So if we do that, Vx, we're going to have it as 0.565 31.64 kilonewton per meter. So that is the load on beam B. All right. So if, for instance, you intend to calculate the load on this particular beam, this will now you now make use of Vxy. That is the load on the short span. Okay. You make use of V. For example, let's say we call this beam C. All right. Let's just calculate the load on that beam C. So we'll make use of the shear force coefficient. So for beam C, it will be Vxy, and it's equal to the beta Vy coefficient for continuous edge. Remember, this is a continuous edge, which represents this direction of the beam, which represents the continuous edge direction of the beam. So Vx becomes Bvy for continuous edge. So the continuous edge Bvy is 0.4. So we have 0.4 times 16.0 times 3.5. If we do that, Vxy for the continuous edge of the short span will be 0.4 times the load there to be 22.4 kilonewton per meters. All right, so this is how you load your beam. So you just take note of the edge conditions, and once you do it correctly, you have all the loads on this beam. All right, so you can load adjacent panels whichever way you want. So I believe with what we have done, you'll be able to do any work on loading of beam using Bs8110 formula and also eurocode 2 formula. Beam B has been loaded. If you look at the beam, you discover that the load is placed at 0.7 L of the span. But for us to make it easier because of analysis, you can decide to run that UDL throughout the span. So we can say that the UDL can be expanded this way, can be expanded this way, can be expanded this way. All right. So once you do that, you have the UDL occupying the entire span. But if you don't want to do that, if you feel comfortably designing with 0.75L, you are okay. But otherwise, it is advisable to load the remaining part of the beam with your load. All right. So with what we have done today, I believe you'll be able to load any beam using the BS8110 and eurocode 2. Thank you very much for watching. Please do well to subscribe to this channel. I'll see you in our next video. Thank you and stay cool.